Welcome, listeners, to Astronomy Daily, your go-to podcast for the latest updates and fascinating facts about space and astronomy. I'm Anna, your friendly host. Today, we've got an exciting lineup of news topics to discuss. First, we'll delve into NASA's remarkable achievement of streaming 4K video footage from an aircraft to the International Space Station. Next, we'll uncover the astonishing discovery of a diamond mantle beneath Mercury's crust. Then, we'll explore the groundbreaking ionospheric insights from NASA's recently concluded ICON mission. And finally, we'll marvel at the James Webb Space Telescope's imaging of a super-Jupiter in the Epsilon Indi system. So, buckle up and get ready for a journey through the cosmos. Recently, a team at NASA's Glenn Research Center in Cleveland achieved something extraordinary. They streamed 4K video footage from an aircraft to the International Space Station and back, marking the first time this has been done using optical laser communications. This groundbreaking technology can transmit data 10 to 100 times faster than traditional radio frequency systems. Imagine the possibilities this opens up for future lunar missions. Historically, NASA has relied on radio waves to send information to and from space, but laser communications utilize infrared light, which can carry much more data at higher speeds. For these tests, the engineers installed a portable laser terminal on the belly of a Pilatus PC-12 aircraft. Flying over Lake Erie, they streamed video data to an optical ground station in Cleveland. From there, the data traveled over an Earth-based network to NASA's White Sands Test Facility in New Mexico. Using infrared light signals, the data was then sent 22,000 miles to NASA's Laser Communications Relay Demonstration in orbit, which relayed it to the ISS and back. According to Dr. Daniel Rabel, principal investigator for the project, this achievement is a tremendous milestone. The success of these laser communication tests lays the groundwork for much anticipated features like high-definition video conferencing for astronauts on the moon during the Artemis missions. Continuous improvement of this technology during each test flight has shown that aeronautics testing can be more effective and cost-efficient than ground or space testing alone. James Demers, Chief of Aircraft Operations at Glenn, emphasized that the goal is to ensure new technologies don't just stay in the lab, but are tested and matured in real-world conditions. These initiatives are part of a broader goal to enable high-bandwidth data streaming from deep space, which will be crucial for future human missions beyond low Earth orbit. While the current hardware setup may conclude its tests soon, the successful trials of 4K video streaming from aircraft indicate a promising future where high-definition video brings us closer to experiencing space missions in real time. As NASA develops advanced instruments to capture high-definition data on the moon and beyond, the capabilities of laser communications will continue to play a pivotal role in bringing space exploration right to our screens. New research using data from NASA's Messenger spacecraft has uncovered a surprising diamond mantle beneath Mercury's crust. Scientists have long been puzzled by Mercury's unique characteristics, like its very dark surface and dense core. By analyzing patches of graphite on its surface, they speculated that Mercury once had a carbon-rich magma ocean, leading to the formation of this diamond mantle. The data suggests that heavy pressures and high temperatures inside Mercury caused carbon in the mantle to crystallize into diamonds over billions of years. This diamond layer could be up to 10 miles thick, providing a completely new understanding of the planet's composition. This discovery not only changes our understanding of Mercury, but also sheds light on its rapid cooling and shortened volcanic era, making it starkly different from other rocky planets like Earth or Mars. Researchers believe that the diamond mantle might have played a role in the planet's fast cooling process, effectively ending its volcanic period much earlier than other planets. This finding exemplifies how unique Mercury is compared to its solar siblings and opens up new pathways for understanding planetary formation and evolution in highly carbon-rich conditions. As scientists eagerly await more data from future missions, including ESA's Bepi-Colombo set to arrive at Mercury in 2026, this diamond revelation continues to intrigue and inspire. NASA's ICON mission has concluded, but what a journey it has been. Launched in October 2019, ICON, or Ionospheric Connection Explorer, has provided unprecedented insights into the ionosphere, the outermost layer of Earth's atmosphere. This region, Nestled between 55 miles to 360 miles above our planet is a bustling zone teeming with charged particles. Studying this frontier has been crucial as it impacts everything from satellite operations to GPS signals. One of the most stunning achievements of the ICON mission was capturing data that showcased the intricate relationship between space weather and Earth's weather. A mesmerizing feature called air glow was extensively observed, helping scientists decode the ionosphere's density, composition, and structure. Unlike the aurora borealis, which paints the polar skies, air glow is a subtle, world-spanning phenomenon created by similar processes. But that's not all. ICON provided the scientific community with its first-ever concrete observations of the long-theorized ionospheric dynamo. This dynamic system of terrestrial winds and space weather interactions generates complex electric and magnetic fields. ICON's measurements revealed how unpredictable terrestrial winds move plasma around the ionosphere, causing charged particles to either shoot out into space or plummet towards Earth. This discovery has been nothing short of transformational. The mission also captured how external events, such as volcanic eruptions, influence the ionosphere. The 2022 Hunga Tonga Hunga Ha'apai eruption, for instance, disrupted electrical currents in this charged layer. ICON's instruments were able to directly observe the speed of this volcanic plume and its far-reaching impacts on ionospheric structures. However, as with all great missions, there came a time to say goodbye. Communication with the ICON spacecraft was lost in November 2022, and despite best efforts, contact could not be re-established. While the mission officially ended, its legacy endures. The wealth of data collected will continue to benefit space and atmospheric science for years to come. ICON has indeed lived up to its name, making iconic contributions to our understanding of the boundary between Earth and space. The James Webb Space Telescope has achieved another groundbreaking milestone by successfully imaging a super Jupiter in the nearby S03E110 system. This monumental discovery is setting the stage for a new era of exoplanet research, allowing scientists to study colder gas giant planets in much more detail than ever before. S03E110, or EPS-IND for short, is a nearby triple star system located just 12 light-years from Earth. The newly imaged planet, designated as EPS-IND-AB, orbits the primary star of the system. Previous studies had identified this planet, but with the data from JWST, scientists were able to correct earlier misconceptions about its mass and orbital path. It turns out this super Jupiter is about 6 times the mass of Jupiter and follows an elliptical orbit ranging from 20 to 40 astronomical units from its star. One of the most exciting aspects of this discovery is that it's the first time a relatively cold gas giant planet has been imaged directly, rather than through indirect methods like transits or radial velocity measurements. By capturing direct images and analyzing the planet's spectra, researchers can study its atmosphere and monitor its evolution, comparing it to computational models. This advances our understanding of planet formation processes and the late stages of planetary system development. The EPS-IND-AB planet, cooler than the gas giants previously studied, showed up in JWST's mid-infrared instrument MIRI images as a bright dot. To achieve this, JWST used a coronagraph that blocks out the blinding light of the host star, making it possible to see the faint light emitted by the planet itself. This method opens new doors to studying gas giants that are otherwise difficult to detect due to their distance from their parent stars. The data also revealed some intriguing characteristics about EPS-IND-AB's atmospheric composition, suggesting substantial amounts of heavy elements like carbon. However, further research is necessary to draw definitive conclusions. In future observations, scientists aim to obtain detailed spectra that will provide in-depth information about the planet's climate and chemical composition. This discovery acts as a stepping stone for hunting more cold gas giants, helping to refine our theories on how such planets form and evolve in their mature stages. So, keep your eyes on the stars and stay tuned to Astronomy Daily for more fascinating insights as we continue to explore the ever-expanding universe. Thank you for tuning into this episode of Astronomy Daily. I've been your host, Anna. Be sure to visit our website at astronomydaily.io to sign up for our free daily newsletter, catch up on the latest space news, and listen to our previous episodes. Don't forget to follow us on social media by searching for Astro Daily Pod on Facebook, X, YouTube, and TikTok. Until next time, keep looking up.